Hello and welcome. This is Chapter 8, which is Dynamics 2, Motion in a Plane. We're dealing with problems with forces where objects are moving in more than one dimension. And in Chapters 5 and 6, we started off with the basic ideas of an object moving on a single line and an acceleration in a single direction. Now we're extending this conversation to objects perhaps moving, not only moving in two dimensions, but perhaps having accelerations in two dimensions. And how does that affect the motion and how we approach the problem? Of course, this loop-the-loop in a roller coaster is a common thing in this example, and vertical circular motion certainly is something in this chapter. As usual, there's these chapter preview slides, which you can read in the book. I mean, are Newton's laws different in two dimensions? And the answer is really no. I mean, it's just how you approach the vector problem with a firm foundation in vectors and Newton's second law. That's really how we're extending this example. Projectile motion actually gets kind of interesting when you include drag in two dimensions, one thing that we might consider. Of course, circular motion is an important topic that we'll return to. We started it in Chapter 4. Now we're returning to it again and talking about the forces that make a single particle. We're still using the particle model. What forces make that object move in a circle? Chapter 12 is where we really extend our idea not only particles moving in a circle, but also entire objects revolving around an axis of rotation. When we talk about orbits, vertical circular motion, and some applications. Okay, so dynamics in two dimensions. Newton's laws determine an object's acceleration. Right, that's what we started out with. And chapters 5 and 6 gave the definition of Newton's second law as a non-zero acceleration means that there is a non-zero net force, right? And the net force and that acceleration, of course, are aligned in the same direction and proportional to each other by a constant proportionality that we call the mass of the object. Remember, this mass is an intrinsic property of an object. It doesn't change with speed or acceleration or location or time, unless it's a rocket burning fuel, but that's a different problem. So the mass stays constant, and Newton's second law is now a vector equation. Now we're going to hold fast to that vector symbol on the acceleration, because we might be dealing with problems with accelerations in both directions. So what's the strategy when dealing with problems like this? Well, you sum Newton's laws and you do just like you would, show the important points in the motion. So this is a model 8.1 for Newtonian mechanics, or no, this is 6.1. This is a review from chapter 6 on Newtonian mechanics and the problem. So you usually model the object as a particle, draw a free body diagram, perhaps an interacting object diagram if you're in chapter 7, sum the forces using the first, second laws. What is this last thing? It's okay to go back and forth between these steps. Yes, definitely, because sometimes you'll see that your free body diagram gives you a minus sign that you didn't know you had, or you have a arrow that points in the wrong direction. That's going to affect the cosine or the sine, and all those things work. And this stuff is only learned by practicing. Okay, so now we can move on formally to dynamics in two dimensions. This is problem-solving strategy. The same thing of the particle model, the solve step, and the assess. Does your answer make sense? Again, typically for problems in chapters 5 through 8, the numbers are not extraordinary. They're somewhere between 1 and 10, or maybe between 10 and 100. So that's the assess step. Okay, here's an example of rocketing in the wind. I mean, you got a rocket that's launched, and how do you model wind, actually? How you model atmospheric effects will decide how complicated the problem gets. So I think in this example, which again, this is something you certainly read on your own, pause the video if you need to, read on your own, try to write it out, try and solve it on your own. But for folks that are continuing, we got a rocket with a mass of 30 kilograms and generates 150 newtons of thrust. Now, so on a windy day, here's the key sentence. The wind exerts a 20 Newton horizontal force on the rocket. Now, how would you figure out that force? That technically, you could get an estimate on that force based on the speed of the wind and also the drag equation, one of the drag equations that you found in chapter 6, whether it's a quadratic drag force or a linear drag force, you can find that. And so you got two net forces, one in the x direction, one in the y direction. And so what you'll need to do is, you know, how far off the launch pad, I think, is it after where it reaches its height of 1 kilometer. And so you can go through all these equations. The thing is that different from projectile motion, now we have constant acceleration in both directions. We have it in the vertical because it's the thrust minus the, it's the thrust minus the gravity. And so the thrust minus the gravity, let's see, I misread it. It's 1,500 newtons of thrust, which actually makes a lot of sense because the 30 kilogram rocket is about 300 newtons of gravitational pull. And so you'll have a net force upward of about 1,200 newtons, technically 1206 newtons. Yeah, because 30 times 9.8 is 294, and 1,500 minus 294 is 1206. All right, it's just 1,500 minus 300 plus 6. These mental math problems are helpful. So that's the net force in the y direction upward. And then you have a net force in the x direction, you know, to the east or whatever. And so you just, to find out how far, you just have to work between, I'm not going to do this in too much detail, but, you know, you have to work between the x direction, y direction, just like you would. This is a fantastic pictorial representation of the figure. It's got the free body diagram, it's got the knowns, it's got the unknowns. Sorry, we had a small technical issue, but we're back. And so again, so we've drawn this picture is an excellent pictorial representation of the rocket as it's being pushed to the right, even though it's accelerating upward. And so the thing is that we have to use the constant acceleration equations in both directions. We have to use it in the vertical and in the horizontal, which is different from the projectile motion problems from chapter 4, because in the projectile motion problems of chapter 4, you didn't need to use acceleration in the x, right? There's nothing pushing or pulling the object in the x in projectile motion, but here there is. And this wind force, fortunately, it's only constant. And fortunately, it's not in the direction of motion. That would make a much harder problem. But we get the net force in both directions, so work acceleration between them, time connects them, and it's probably best if you just kind of go through it yourself and verify that you know the answer. So I'm going to skip through this. It's good discussion here, but let's move on. And speaking of projectile motion, we have a review of projectile motion. Now we typically use a standard XY coordinate system. That's going to leave us with acceleration that's constrained in the y direction, right? We typically, if we choose the typical up is positive y and to the right is positive x, then the net force is only just mg down. And so if you just equate mg vector in the j direction minus technically, that equals ma, and so your acceleration is the expected value of minus g in the j direction, because the acceleration in the x direction is 0, like that equation at the bottom says. So there's not really much to do new in these projectile motion problems when you're ignoring air resistance. When you include air resistance, and in this example, the range equations, we have these pictures where the where the range is the same for complementary angles, such as like 30 and 60 give the same range, 75 and 15 give the same range, 45 is, of course, the angle of maximum range. But that is only when drag is not included. If you go in the textbook, you'll see a derivation that uses the quadratic drag model. If you remember quadratic drag model, that is F equals 1/2 rho CA times velocity squared. And if you do that, and if you go through this derivation, you get a pair of equations for the acceleration in the x direction, acceleration in the y direction. And these are not equations that you want to try and solve by hand. And it really gives a general theme about solving some of these problems, that just adding a small layer of difficulty, a small layer of realism to the problem makes it essentially unsolvable with pencil and paper. That's the bad news. The good news is there's plenty of computing power to do that. I mean, this problem by itself can be handled to a couple of significant figures on a laptop. Modern problem, trajectory type problems that include, that include drag forces, that include moderately changing gravity, that include changes in density of air and atmospheric pressure. Those are all like lots of different equations, and those are all shoved into, I don't want to say shoved, but those are all well documented, and you use high performance computing systems to handle that. At Wichita State, we have a high performance computing system that can technically handle problems of that magnitude. But in this, what you do is you find that the acceleration in the x direction actually depends on the velocity in both directions. And the same thing in the y, but including g. All that to say, I don't want it to get lost on us, but it turns out that when you include drag, then 45 degrees is actually not the angle of maximum range when you're flying off a horizontal surface. And that becomes very interesting. And it turns out that the range, the angle of maximum range, there's not an easy way to find it, but numerically, you can show that, angles close to 15 or 20 degrees will typically give maximum range. Now, why is that? Because if you look at the forces acting on the object in the air, there's always, the range. You get the range by the velocity in the x direction, right? The range literally is the velocity in the x direction times the time of flight. Well, you might think that if it's in the air longer, it's got a longer time of flight. Okay, that's true. But with the drag force pointed against the direction of motion, there's always a small force against the horizontal motion. If the particle's moving to the right, if you look at these trajectories, if the particle's moving to the right, there's always going to be a small component of the drag pointing to the left. So it's always going to slow down. And so if you shoot up very high, the drag force will almost immediately accelerate the horizontal motion to zero. And then, so for instance, professional PGA golfers, one example of professional golfers is that they have their launch velocities of their, driver tees to be about 50 meters per second, which is about 110, 115 miles an hour. It turns out that those angles of maximum range tend to be around 12 to 14 degrees. And it's a complicated problem with many different variables, but evidently the 10 to 15 degree range of the launch angle tends to be the reasonable choice for getting the ball to go as far as you can, because the ball's, when you shoot at that shallow of an angle, then it has lots of opportunity to slow down because it's got a very high initial x velocity. Of course, you have to also compare that with high enough y velocity such that drag doesn't slow down that. So several different things to consider. It's a really interesting one. So baseball players, I mean, anyone on a, high projectile sport should be aware that 45 isn't necessarily the fastest angle or angle of maximum range when you're doing drag. So that's another topic. This first section is kind of a broad overview of two-dimensional dynamics. And as you can tell, in general, I mean, these problems are pretty hard to solve. And so we'll stick with some problems that are a little bit more basic, especially ones that are involved circular motion. So that concludes this video. Thanks for watching. In the next video, we'll talk about uniform circular motion. Thanks for your time, and take care.